Hello everyone, my name is Adriel and I'm going to present an article entitled Milling and Magnetic Abrasive Finishing of Directed and Deposited 316L stainless steel, which was co-authored by Iago, Professor Heraldo, and Professor Reginaldo. Additive manufacturing, AM, is a technology for building three-dimensional parts layer by layer. It has been considered a high-potential disruptive technology with significant increase in the recent years, and is present in the most diverse manufacturing industries, for example, automotive, aerospace, medical, oil and gas, and others. The American Society for Testing and Materials, ASTM, classifies AM technologies in 7 groups, being applied for metals, polymers, ceramics, and composites. The techniques that stand out for metallic components are powder bed fusion, PBF, direct energy deposition, DED, and sheet lamination, SL. Each one has its peculiarities, and the choice of which process to use depends on the request and necessity of the component to be manufactured. The DED process combines material feedstock and energy for layer-by-layer deposition, hence formation of the part. This figure shows an illustration of the process, which involves powder as raw materials and lasers as heat source to create a melt pool. With nozzle movements, the layers are being deposited until the workpiece is formed. The DED can be applied for repairing, coating, functional graded materials, multi-materials, and others. However, both dimensions and surface quality of parts are relatively poor, requiring post-processing operations to overcome those limitations. Depending on the application of the component, traditional machining process, for example milling, or even some advanced finish process, for example magnetic abrasive finishing, MAF, are therefore necessary for the obtaining of the desired functional performance. As milling is a well-known process, on the next slide I will explain a little about the MAF process. MAF mixes magnetic abrasive particles and abrasive in a magnetic field between poles and the workpiece itself. The material is slowly removed through magnetic forces and relative movements, improving surface quality. The applications and advantages of this process are the possibility of controlling the magnetic forces involved, the ability to polish internal and external surfaces in the same time, also parts with different geometry, for example flat, cylindrical, and complex, for example knee prostheses, and difficult to access, for example needles. The process is simple and economical. However, there are some limitations, such as low material removal rate when compared to other non-traditional machining processes, and consequently high processing time. Regarding post-process operations of parts made using AM, depending on the application, we can apply only a process, for example milling or MAF. Although using only MAF, the process time could be high and some shape errors may not be removed. For some additively manufactured parts, milling operations may be necessary prior to the MAF for correcting geometric and dimensional errors, since the physical nature of the process is a motion copying process does not correct them. So it's necessary to study the manufacturing process chain in order to reduce the steps involved and consequently reducing manufacturing costs and time. It is in this scenario that this article intends to contribute scientifically. Therefore, this study aims to evaluate the impact of milling and MAF operations in the surface quality of 316L stainless steel produced by DED, as well as the effects of process on surface morphology and roughness. A manufacturing sequence was proposed and involves AM, DED, milling, and MAF, successfully applied for improving surface roughness up to nanometer levels. Regarding DED, workpieces shaped as rectangles were deposited using a zigzag strategy. Here we can see a photo. Here we can see other conditions on the slide. After deposition, end milling was carried out. The conditions are shown on the slide, and 3 different cutting speeds values were tested: 300, 400, and 500 meters per minute. And the parts machined under those conditions will be referred to as M300, M400, and M500 respectively. After milling, MAF was carried out. 3 neodymium magnets were used to create the magnetic field, rotating at 500 RPM. You can see here on the video. A mixture of iron particles and abrasive slurry was made, and also a linear movement strategy was adopted, deploying an oscillation on x-axis with +5 and -5 millimeters from the center, using a feed rate equal to 1 millimeter per second. Each sample was polished at 5, 10, and 15 minutes. So the parts will be referred to as MAF5, MAF10, and MAF15 respectively. Other conditions are shown on the slide. This figure shows the general aspects and the surface morphologies of the parts after each manufacturing process. After DED, the contours of deposition beads are visible. Here you can see the deposition lines, and some voids and adhered powder were present on the surface, worsening the surface quality. After milling, the surface has typical cutting marks. Here we can see these milling marks here, which is inherent to the process. Finally, the surface after the MAF process has a mirror appearance in which the milling marks have been smoothed and rivet removed. A new texture has arisen due to the abrasive workpiece interaction, showing fine directional patterns parallel to the abrasive sliding directions. Here we can see this. This figure shows the roughness values obtained after each process. Here DED, the 3 conditions of milling, and the 3 conditions of MAF. It can be seen that the surface roughness RA was reduced from 56 to 0.0 microns by M300 and to 0.03 microns by MAF15, indicating more than 99% improvement. Regarding the RZ values, there was a reduction for more than 240 to 0.56 microns by M300 and to 0.23 by MAF in all conditions, also showing more than 99% improvement. The high roughness values of parts manufactured by DED is due to the deposition beads morphology and geometry, and the presence of partially melted powder particles adhered to the surface in other factors. During milling operations, despite the presence of some edge marks, the roughness values were provided at nanometer levels. After MAF, surface quality was improved, in which roughness values were minimized and surpassing those achieved by milling. The line in black represents a processing route adopted by a reference study in the area, published by Yamaguchi. 4 hours of processing time were spent on the reduction of RZ from more than 100 to 0.01 microns. The line in red represents the processing route adopted in this study. The RZ of the parts presented here are more than twice that of reported by Yamaguchi. Under the same processing conditions, near 5.5 hours or more would be necessary for the achievement of the same surface quality. However, using milling as an intermediate process step between the deposition and finishing process, the total processing time was only 22 minutes. Therefore, the achievement of low roughness values in shorter manufacturing times requires milling be used prior to a finishing process, since it has proven efficient in reducing the overall processing time. So, the conclusions. DD produced a rough and irregular surface contributed by the presence of adherent particles and bead profiles. The irregularities of the outer layer were completely removed by milling, reaching nanoscale surface roughness, with typical cutting-edge marks on the surface. These milling marks were removed by MAF, further reducing roughness values. The whole sequence time for the production of a polished surface, which involved DD, milling, and MAF, was near 22 minutes. Compared to a research article with no milling, the time would be around 5.5 hours. So, milling used as an intermediate processing step between deposition and finishing process has proven efficient in reducing the overall processing time and the manufacturing sequence of parts obtained by additive manufacturing technologies. Here the reference used in this presentation. My acknowledgements to USP, Lapras, FAPESP, Plaza, and Sangoban. Thank you so much. Now I'm open to questions. Here my mail. Thank you. Keep safe.